All right, this is the myAP problems, 3.5 and 3.6, and I'm just going to talk through. I'll probably make like 3 videos, so they're not too long. Yeah, so I'm just going to start talking through these. So a randomized block design will be used in an experiment. So block design, that's a key word there to compare 2 lotions that protect people from getting sunburned. So block means you're going to run the same experiment multiple times. Usually it's twice, once on each subgroup. And you want the subgroups to be as similar as possible. So in this case, what I would do is D. I would want each block to be as similar as possible with respect to how easily they get sunburned. So if I got a bunch of fair-skinned people, and I'm just going to say like fair and not fair-skinned, we can get a lot more in detail, but I'm going to give half of them the new sunblock, or the one lotion, and half of them the other lotion. I'm going to give half of them one lotion and half of them the other lotion. So I have these 2 blocks or 2 subgroups, and I want to run the same experiment twice, in this case, on those 2 subgroups. And the reason for that, or the benefit of that, is it might be that this new sunblock or new sun lotion really works well on people without fair skin, but not on people with fair skin, or vice versa. And if it was all blended together, we wouldn't really be able to tell that. So the biggest thing here, and you're going to get this from the lectures too, but block means similar subgroups. So you want similar subgroups, and then you run the experiment twice, or it could be 3 times on each of those blocks. Number 2, there are 4 things that should be in any well-designed experiment. One is control, and that means you have something to compare it to. Sometimes, so a lot of people think of control group like a placebo, where you don't do anything. Like I'll take half the people and give them this new drug, and half the people and give them a placebo. That is a control group, but it doesn't need to be like you do nothing. So it could be that I'm going to cook this chicken for 20 minutes, and I'm going to cook this chicken for 30 minutes, and I'm going to compare. That's control, because I have something to compare it to. But a control group, as far as like a placebo in that situation, I'm not going to cook a chicken for 0 minutes and do anything with that. Randomization, the subjects, the chickens, whatever it is, have to be assigned to the groups randomly. Otherwise, you get bias. And then at the end of any experiment, you want to compare the results. And this wasn't one of these 3 one of the options here, but all 3 of these are true. That's these 3, and then there is a 4th if you ever asked about it. Number 3, florist wants to tell whether a new powder keeps them fresh. So for each shipment of roses, we're going to flip a coin. Why would we flip a coin? Well, because we're trying to randomize it. Otherwise, if I start, like I'm going to put these over here, my bias, my brain comes into it. I don't want my brain. My brain is not fair. It has biases in it. Nobody's brain is fair. Everybody's brain has biases in it. So I'm flipping a coin that randomizes things. And then half the flowers are going to get the new powder, and half of them won't. So I did not split into subgroups. I just randomly mixed up, half go here, half go there. So flip a coin, you get the new powder, you get the old powder, new, old. At the end, we compare the results and we see what's what. So that is completely randomized. We did not split into subgroups. Number 4, so they read all that paragraph is on there, but then they get to this question: what is the confounding variable? So a confounding variable is a variable that you are not measuring, but it's behind the scenes and it's super important. The most common example of that would be something like if I put number of churches in America, let's say. And then here I put number of murders. And then I go like from 1600. No, I don't do that yet. And I look at, okay, if I did this, if I graphed this data over time, this is what it would look like. So would I say then that churches are causing murders? Absolutely not, because there's a confounding variable in here that as time has gone by in America, more people have lived here. So at the beginning, there weren't a lot of churches and there weren't a lot of murders. Now there's a lot of both, but there's no cause there. I didn't randomly split anything. I didn't control anything. This is not an experiment. I cannot show a cause and effect. what's happening is there's a confounding variable behind the scenes that is impacting things that I'm not taking into account. In this case, it's time, or population, I guess you would say. So what's the confounding variable in number 4? Well, the problem is in number 4, it doesn't say. So you would need to randomly assign these. You would need to say, I'm going to randomly choose. I got 50 people. I randomly choose 25 and flip a coin. Randomly decide who gets the spin class, who gets the aerobics class, and then all the confounding variables are mixed up into 2 groups. I got my 2 groups, and then if one of them does better, I know that was the reason. The reason that not randomly assigning is a confounding variable is because it could be true that people that choose aerobics classes compared to people that choose spinning classes might be different in some way that matters when you're talking about body fat. Maybe people that are in spinning tend to be like super fitness freaks and they don't eat unhealthy foods and they exercise 7 times a week and blah, blah, blah. And it might not be the case, but the fact is you're letting them choose which one, and that is not ideal. What we want to do is randomly assign it, and we didn't. So number 4. So the confounding variable is the participant's choice of which class to take. All right, number 5. I put these 2 lines in there, and now I don't know how to get rid of them. Maybe this. All right, number 5. Defective items produced by workers. 30 workers agree to participate in a study of 3 different incentive plans. So 10 workers in each plan. We're going to count and see if any of the plans helped reduce defective items at all. They are randomly assigning the workers. So there are no subgroups. There's no subgroups, there's no blocking variable. They're randomly assigning to groups, and that's it. So a third of them get each of the incentives. We compare at the end and see which one worked better. Part D is kind of tempting. Each plan will be randomly assigned, that's good, to 10 pairs of workers, and that's not what, so 10 pairs of workers would be like 20, and that's not what's going on here. So, all right, number 6. So a lot of these are just so freaking wordy, and for me, and my guess is some of you are similar and some of you are different, but when I see this, my brain just like, it just freezes, and I'm like, I need to get this out of this gigantic paragraph. Reading is not my thing. So I started like kind of underlining and just making notes. So we want to study a certain chemical on cell growth. We got 2 different doses, high and low, and 2 different cell types, A and B. So what we got there, just to sketch this out, you got high dose, low dose, and then you got strain A and strain B. So you actually have 4 different treatment groups going on there. Each combination is to be replicated 10 times, so you got 10, 10, 10, 10. To have this sentence just blew my mind. To have consistency from one replicate to the next, the researcher decided to use, that should be 1. If you use 1 lab technician, that is consistent. It is the same every time. If you use 4, it's not. So I might do something differently than Mr. Bud if he's a lab technician, do something differently than Bartnicki if she's a lab technician. If you want consistency, you want the same thing every time. So I'm not going to assign a different lab technician here. I'm going to assign the same one every time. So the lab technician is a confounding variable. This person might measure things, treat things, do things differently than this person, than this person, than this person, and that's not good. Number 7. We're going to do a 5-pound cut of lamb. We're going to test 45 minutes. We're going to test 60 minutes. We're going to test 90 minutes. We're going to do 350 and 425. And we're not doing the 90-minute 425 combination. Apparently that's too much. So we got 10 cuts of lamb. 2 go there, 2 go there, 2 go there, 2 go there, 2 go there. Which of the following is true? Number 7. So it says the explanatory variable is the quality of the land. That's false. It's a response variable. That's the quality of the land. The response variable is the output, what you measure at the end. It says the response variable is the roasting temperature. That's false. The explanatory variable is the roasting temperature, because that's what we're trying to measure. If it was repeated, identical results would be expected. Identical is a really strong word. You'll probably get similar results, but you will not get identical, or you're very unlikely to. There should be a control group. So there is control in this experiment because you are comparing, but there doesn't need to be a control group, because what are you going to do? Not cook it? I mean, obviously that's not helpful, so we don't need to do that. And then the fact that we're doing 2 for each time temperature combination is replication, so we're doing it multiple times. And I'm going to stop there. So that's 1 through 7. That's about 10 minutes.